Hello everyone. In this lecture I shall discuss the Runge methods, and basically I will compare this method with the previously discussed Euler's method and Taylor series method. Now if you recall the Taylor series method, the major disadvantage is that it requires the partial derivatives of higher orders, which is laborious and lengthy, and sometimes for complicated functions it is not possible to find the Taylor series expansion up to higher degree. So however, the Runge methods do not require derivatives, and these methods also agrees with the Taylor series solution up to the term h to the power r. As I have told you, Taylor series is the Runge method of order 1 agrees with two terms containing up to the power h to the power 1, right? So now this up to h to the power r, where r differs from method to method, is called the order of the method, right? It's called the order of the method. So moreover, the accuracy of the RK method is high, and basically the RK method of order 4 is very high, and by saying Runge method, it is only the Runge method of order 4 which is exactly the RK method only, right? And we see the Runge method of first order of order 1. As I have pointed out earlier, suppose you are given a first order differential equation dy by dx is equal to fxy with initial condition y of x0 is equal to y0. By Euler's method we know the necessary formula is yn plus 1 is yn plus hf xn yn. This method agrees with the Taylor series up to the h to the power 1 term, right? That means you have your Taylor series is yxn plus h is yn plus h y dash xn, right? So now y dash is what? hf xn yn. So this Runge method of order 1 agrees with the Taylor series up to the power of h to the power 1, right? Hence the Euler method is known as the Runge method of first order, right? So before the subsequent discussion of second order, third order and fourth order, let me to introduce myself. Myself Professor Kumar Paikray, currently working as a Professor of Mathematics at Veer Surendra University of Technology Burla in South Visut, Odisha, India. So without much delay, let me to discuss the other higher order methods. Now coming to the RK method of second order, right? Also this method is known as here, this method is same as here improved Euler method, right? It's same as here improved Euler method, or it is also here Hume's method, or it is also here Euler-Cauchy method, right? Cauchy method, we can say improved version. So right, so this improved Euler method is same as here RK method of order 2. Already have discussed it in my previous lecture. So the improved Euler method is given by the formula, you can refer the previous lecture, is given by the formula this. That means what is your Euler's method? Euler's method is nothing but the equation of the tangent line in a given interval with the slope at the initial point of the interval, right? But here in RK method of order 2, what we are doing? We are taking the slope, average of the slopes at the initial point and the end point, okay? And the necessary formula is given by this. Yn plus 1 is yn plus k1 plus k2 divided by 2, with k1 is hf xn yn, right? And k2 is just hf xn is incremented by h, means xn becomes xn plus 1, and yn is incremented by yn plus k1, okay, incremented by k1. So this is the necessary formula for RK method of order 2, right? For solving the problem, just remember the formula without going deep into the theory. But for the deep learners, the basic correlations and the theory is essential. Okay, and this method agrees with the Taylor series up to h square term, right? Up to h square term, that is yxn plus h is yxn plus h y dash xn plus h square by 2 factorial y double dash xn, or I write in short yn. Okay, so now thus the improved Euler method is RK method of order 2 because it agrees with the h to the power 2 term. Okay, now coming to the RK method of order 3. RK method of order 3, it is developed by the German mathematician Runge. Okay, and it is German mathematician Runge. So this method is named as Runge's method, and it agrees with the Taylor series up to h to the power 3 term. Okay, so the necessary formula for RK method of order 3 is given by this. Yn plus 1 is yn plus 1 by 6, means in Taylor series methods, in your Euler's method we are taking the slope at the initial point. In improved Euler method we are taking the slope, average slope of the initial and the midpoint, initial and the terminal point, and here we are taking the weighted slope, right? 1 into k1 plus 4 into k2 plus 1 into k3 divided by 6. We are taking the weighted slope, right? So here we have here k1 is given by this hf xn yn, k2 is given by this, it is just xn is incremented by h by 2, yn is incremented by k1 by 2. K1 is here already. Okay, k1 is here. So now, and what is your k2? It is here hf xn plus h incremented by h, and yn plus, I write some k1 dash, k dash, and k dash is this. Okay, we have to find first k dash, means hf xn plus h y0 plus k1, right? So we find k dash and we substitute here, right? Then coming to the Runge-Kutta method of order 4, right? So it is also called the classical RK method of order 4. The method is named as Runge and Kutta because it is the contribution of two authors. Earlier the Runge obtained the formula, as we discussed, the RK method of order 3, the German mathematician Runge. So 1856 to 1927, and again the William Kutta, okay, extended this. So jointly this method is known as the Runge-Kutta method. Okay, however the method due to Runge is the Runge's method of order 3, and later on jointly these methods are named as Runge-Kutta method of order 1, order 2, order 3, order 4. However, this method, this Runge-Kutta method of order 4 is the Runge-Kutta method only. If it is solved by the Runge-Kutta method, we mean that it is only the order 4 unless until it is mentioned that whether it is order 1 or 2 or 3. Okay, so there are several approaches to solve this method. However, the classical approach is given by this. So yn plus 1 is yn plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. You see, 1 into k1, 2 into k2, 2 into k3, k4, means weighted average. Here it is 1, here it is 2, here it is 2, here it is 1. So 1 plus 2 plus 2 plus 1 is 6. So we are taking the weighted average of the slope. If we understand it here, if we understand it geometry. So here k1 is hf xn yn, k2 is here xn is incremented by h by 2, and again yn is by k1 by 2, and k3 is hf xn is incremented by h by 2, and yn is incremented by this previous k2 by 2. Okay, and finally k4 is xn hf xn plus h, and yn plus the previous one k3. Okay, so you should remember the formula. Now if we compare with the previous methods with this geometrical interpretation, as you know, the RK method use weighted average of slopes in the given interval, right, instead of a single slope. Now if you recall, the geometrical interpretation of earlier methods having the single slope, your Euler method is approximated by the tangent line, right, at the initial point of the interval, initial point of this interval. And this backward Euler method is by the tangent line with slope at the terminal point, okay. Here at the point xn plus 1, we take the slope at the terminal point. This method is called the backward Euler's method, right. And your Euler and your modified Euler method, what is known as the polygon method, we are taking the slope at the midpoint of the interval, right, xn plus 1 by 2. Now your improved Euler method or Hume's method, we are taking the average of the slope at the initial point of the interval as well as at the final point of the interval, terminal point of the interval. The error of these two methods is almost the same, right. So few authors confused to say that these two methods are same. Indeed, they are different. These two are different, okay. These two are actually different, right. These two are actually different, the modified Euler's method and the improved Euler method. However, if we approach to a problem, we are getting almost the same answer. So if we see the another approach to the Runge Kutta methods, suppose you are given a first order differential equation, the deep learners can go through this. Otherwise, just recall the formula and solve the problems. Consider the first order differential equation, okay. So in the given interval xn and xn plus 1. Now if you integrate it within the limit xn to xn plus 1, now here dy is fxy dx. Now if you integrate it, okay, from this limit xn to xn plus 1, then what we are getting? This becomes here y. So upper limit is y xn plus 1 means yn plus 1, and this is y of xn, bringing to right hand side it is y xn plus, if I apply the mean value theorem here, it is hf xn plus theta h plus yn plus theta h, where theta lies in between 0 and 1, okay. Now if you put theta is equal to 0, you see, then it is simply yxn, fxn and yxn. So it is here yn plus hf xn yn, right. So is it not your Euler's method? Okay. Or as we have pointed out, it is the RK method of order 1, as it coincides with the Taylor series up to the term in the power of h to the power 1. Now if you put theta is equal to 1 here, you see, then it is xn plus h and it is y of xn plus h, means it is incremented by xn is incremented by h, so it becomes here xn plus 1. So then it becomes here backward Euler's method, okay. Backward Euler's method given by the formula yn plus 1 is yn plus k2, where k2 is obtained as follows: hf xn plus 1 yn plus k1, some extra term k1, with this k1 is obtained by this formula, okay, with this formula. Now coming to the modified Euler's method, if I substitute theta is equal to half, right, then we get the modified Euler's method, as I pointed out, taking the slope at the midpoint of the interval. And this modified Euler method is given by the formula. Also in the previous lecture we have discussed yn plus 1 is yn plus some k2, where k2 is obtained by this hf xn incremented by h by 2 and yn incremented by k1 by 2. And with this k1 is extra here, this k1 can be obtained by this hf xn yn, okay. Now thus this modified Euler method yields the tangent line, as I have told, at the midpoint xn and xn plus 1. This is at xn plus h by 2, which is not a nodal point. xn plus 1, x0, x1, x2, these are the nodal point, not a nodal point, right, not a nodal point. Now if we approximate the slope xn plus 1 by 2 as the midpoint of the slope at the initial and terminal point, okay, then this modified Euler methods agrees with here improved Euler method, right? However, these two methods are actually same, and the formula for your modified your improved Euler method, basically it is known as the RK method of order 2, Runge-Kutta method of order 2, and the formula is, as I have told you, yn plus 1 is yn plus k1 plus k2 by 2, where k1 is hf xn yn and k2 is hf xn plus h and yn plus k1 is here. Okay, so however, the modified Euler's method is a polygon method and it is different from your improved Euler method. Okay, it is different from your improved Euler method. So this is the another approach from the Runge-Kutta methods point of view. The previous methods are being compared. Okay, so now you should remember the formula only. Okay, for solving the problem you should remember the formula only. Here this is your Runge-Kutta method of order 2 and this is your Runge-Kutta method of order 3 and this is your Runge-Kutta method of order 4. You will remember these three formula and accordingly solve the point. However, the interested learner can see the geometrical interpretation and all details. Now let us solve some examples, then we can understand the importance of these methods, in which method we will get the less error. So let us see one example to understand all these things. The example is given the first order differential equation with initial condition. We have to find y of 0.2 by taking h is equal to 0.2, means only we carry out one step. Okay, if I take h is 0.1, then we have to carry out two steps. So I will just carry out one step taking h is equal to 0.2. We solve it by RK method of order 2, then by order 3, then by order 4. Also we solve this differential equation by the usual technique and we compare the difference and we estimate the error in each case. Okay, so let us solve this. So you see, this implies here dy by dx plus minus 1 into y is equal to x. It is of the form y dash plus pxy is here qx. It is a linear differential equation. Linear differential equation, is not it? So what is it? It is my p, it is my q. The integrating factor is e to the power integral p dx. So is equal to e to the power integral minus of dx. So it is e to the power minus x. Then the general solution is y into integrating factor is equal to integral q into integrating factor plus some constant. Okay, so that means here x into e to the power minus x plus some constant. If you integrate using by parts, here x minus e to the power minus x, put a negative sign, the derivative of x is 1, the integration of this is again here minus of e to the power minus x into minus, so it is minus x plus some constant. Okay, so it is minus e to the power minus x taken common, x plus 1 plus c. So now bringing this e to the power x to this right hand side, so this implies here y means y of x is equal to this e to the power minus x cancelled with this, it will here minus of x plus 1 plus here c e to the power x. Okay, so now we substitute the initial condition. Now the condition is y of 0 is equal to 1. So when x 0, y is here 1. So y is here 1 is equal to x is 0. It is minus of 0 plus 1 plus c e to the power 0. So this is equal to minus 1 plus c into 1. Okay, bringing 1 to this side. So that means c is equal to 2. Now you substitute the value of 2 here. Value of c as 2 we are getting. So therefore y is equal to minus of x plus 1. Okay, I rather write y of x is equal to. So it is this plus 2e to the power x. Okay, so this is my actual solution. But the actual solution we need at 0.2. So y of 0.2, if you substitute, this is minus of 0.2 plus 1 plus 2 e to the power 0.2. It will be here 1.2428. So this is the actual solution. Okay, This is your actual solution. Now let me to solve it by using the RK method of order 2. Now by RK method of order 2. RK method of order 2. So what is your y dash is equal to fxy. What is fxy? Fxy is equal to your x plus y. x0 is equal to your 0. y0 is equal to 1. h is equal to 0.2. So the necessary formula is yn plus 1 is equal to yn plus k1 plus k2 by 2. k1 plus k2 divided by 2. We need to find k1. What is k1? k1 is hf xn yn, and k2 is hf xn plus h and yn plus k1. Okay, so now if you simplify it, here only we have to carry out only one step only, because only here h is 0.2, we have to find y of 0.2, so only one step we have to carry out here. So here I can say here n is equal to 0 only, right? We need to find y1 only. So here what is your k1 now? So k1 is equal to here hf x0 y0. So this is h is here 0.2, it is x0 plus y0. So x0 value is 0, it is 1, so it is here 0.2 into 0 plus 1. So this is here 0.2. So the value of k1 is 0.2. Now what is your k2? K2 is hf x0 plus h y0 plus k1. So this is equal to hf x0 is 0 and h is 0.2 and comma y0 is 1 and k1 is this, it is 1.2. So this is equal to here, h into means 0.2 into x plus y, 0.2 plus 1.2. If you simplify it, it will be here 0.28. It will be here 0.28. Okay. Now what is your y1? Now y1 is y of x1, means y of 0.2 is equal to here y0 plus k1 plus k2 divided by 2, and y0 is 1 plus k1 is here 0.2 plus 0.28 divided by 2. So this is equal to 1 plus 0.48 divided by 2 is equal to 1 plus 0.24, and this is equal to here 1.24. So your y1 is 1.24. Okay, means y of 0.2 is this by RK method of order 2. RK method of order 2. Now we see by RK method of order 3 or the Runge's method. Now by RK method of order 3, or what we call it, Runge's method. Okay, so what is the necessary formula? The necessary formula here is yn plus 1 is equal to yn plus 1 by 6 k1 plus 4k2 plus k3. Okay, and what is your k1? K1 is equal to hf xn yn, and here only we have to perform only one step, because here fxy is equal to x plus y, x0 is equal to 0, y0 is equal to 1, h is equal to 0.2. So x1 is x0 plus h is 0.2. We need to find y of 0.2 only. So we have to perform only step 1 only. Okay, k1 is this, and here k2 is hf xn plus h by 2, here yn plus k1 by 2, and here k3 is equal to hf x0 plus h some y0 plus some k dash, and this k dash is with this k dash is equal to hf x0 plus h and y0 plus k1, means xn, I mean to say here xn. And here this method as we need on the result in one step, so here n is equal to 0 only. Okay, n is equal to 0 only. So now what is my k1 with this? What is my k1? So my k1 is hf x0 y0. So this is equal to h into x0 plus y0. So this is 0.2 into 0 plus 1, this is 0.2. And here k2 is equal to here hf x0 plus h by 2 and y0 plus k1 by 2. So this is equal to here hf 0.1 to here 1.1. Okay, so this is equal to 0.2 into 0.1 plus 1.1, and this will be here 0.24. Then here k dash, you find k dash, it is here hf x0 plus h and y0 plus k1. So this is equal to here hf 0.2 and it is here 1.2. So this is equal to h into 0.2 plus 1.2 and it will be here 0.28. Now we substitute it to find our exactly k3. k3 is hf x0 plus h y0 plus k dash. So this is equal to hf 0.2 and it is 1 plus 0.28. This k1 is substituted here. So this is equal to hf 0.2 1.28. So this is equal to 0.2 into 0.2 plus 1.28 and it will be here 0.296. So the value of k1 is this, value of k2 is this, value of k3 is this. Now we have our Runge's method. Okay, so therefore here y1 is y of x1 means y of 0.2 is equal to y0 plus 1 by 6 k1 plus 4k2 plus k3. If you simplify it, so this will be 1 plus 1 by 6, the value of k1 is 0.2, 0.2 plus 0.24 plus 0.296. Okay, if you simplify it, it will be here 0.2426, right? So y of 0.2 is this by RK method of order 3, by RK method of order 3. Now if we see the comparison, now by RK method of order 4, by RK method of order 4. Okay, what is the necessary formula? The necessary formula is yn plus 1 is equal to yn plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Okay, here k1 is hf xn yn, k2 is hf xn plus h by 2 yn plus k1 by 2 and k3, this is k2 is equal to k3 is equal to hf xn plus h by 2 yn plus k2 by 2 and here k4 is hf xn plus h yn plus k3 only. Okay, so here fxy is equal to x plus y, x0 is equal to 0, y0 is equal to 1 and incremented by 0.2h. So therefore x1 is equal to x0 plus h is 0.2. So we need only one step, that's why here n is equal to 0 only. Okay, so for n is equal to 0, and what is your k1 is equal to hf x0 y0, as we did it, it is 0.2 and k2 is equal to hf x0 plus h by 2 y0 plus k1 by 2. If you simplify it, it will be here hf 0.1 1.1 and it is 0.2 into 0.1 plus 1.1 it is 0.24. Then coming to your K3, HF x0 plus h by 2 y0 plus k2 by 2. So this is equal to 0.2 into f of 0.1 1.12. So this is equal to 0.2440. And coming to your K4 is HF xn plus h y0 plus k3. So this is equal to 0.2 into f of 0.2 1.244. So this is 0.2 into 0.2 plus 1.244. So this is equal to 0.2888. Okay. So therefore here y1 is y of x1 means y of 0.2 is y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Okay. So this is my k1, this is my k1, this is my k2, this is my k3, this is my k4. I substitute all these things. So it will be, if I calculate it, I will be getting 1 by, this is 1 plus 1 by 6, 0.2 plus 0.2 into 0.24 means 0.48 plus 0.448 plus 0.2888. Okay, if I simplify it, it is 1 plus. So this is equal to here 0.2428. Okay, so this is y of 0.2 is this, and it is by RK method of order 4. Okay, so now let us compare this and find the error in each case. So by the actual calculation we got, it is 1.2428. Okay, so you see what is the error here. By RK method of order 2, you see this is 1.24, this is here. By order 3 we have 1.2426, so we find the error here, and it is same, there is no error, so we calculate the error. Now we see the error. The error is actual solution minus numerical solution. This is the actual solution, and in RK method of order 2 it is 0.24. So what is the error here? It is 0.0028. And what is the error here? Actual minus numerical. So it is 0.0002. And what is the error here? The error is 0. Right, you see. So this is by RK method of order 4, the accuracy is quite high. Okay, accuracy is very high, right? So though there are several methods of RK method of order 1, 2, 3 and 4, but this is the joint effort of Runge and Kutta, right? So this is the actual Runge Kutta method. If only I solve by Runge Kutta method, we mean that it is the method of order 4 only. Okay, now let us solve one more example where we carry 2 steps to get the answer. Now you see, we are given this differential equation, y0 is equal to 1, and we have to find y of 0.2 taking h. Means I mean that solve in the interval, 0 0.2, because we start at 0 here, and we have to get y of 0.2, right, with the increment h is equal to 0.1. so we need 2 steps here. Okay, so now coming to the solution, fxy is equal to y minus x by y plus x, and x0 is equal to 0, y0 is equal to 1, let h is equal to 0.1. So here it is given h is equal to 0.1, or we find of our own. If I take h is equal to 0.1, if I take h is equal to 0.1, it needs 2 steps. If I take h is equal to 0.2, it need only 1 step. Okay, so if h is not specified, then the choice is up to us. Okay, that means if h is not given, you take it as your own choice, whether you will take 0.1 or 0.2. Now coming to the solution, So this implies what is my x1? x1 is 0.1 and x2 is 0.2. So we reach at the destination. We want to find y of 0.2. So now coming to the necessary formula for RK method is yn plus 1 is equal to yn plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. We need to find k1, k2, k3, k4. k1 is hf xn yn, k2 is hf xn plus h by 2 yn plus k1 by 2, k3 is hf xn plus h by 2 yn plus k2 by 2, and here k4 is hf xn plus h yn plus k3. So here h n greater than is equal to 0. So coming to step 1 for n is equal to 1, what is your k1? k1 is hf x0 y0. So this is equal to h into your y0 minus x0 by y0 plus x0. You substitute it, it is 0.1 into 1 minus 0 by 1 plus 0. It is here 0.1. Okay. Now k2 is hf x0 plus h by 2 y0 plus k1 by 2 is equal to hf 0.05 1.05. So this is equal to 0.1 into 1.05 minus 0.05 divided by 1.05 plus 0.05. If you simplify it, it will be 0.091. Okay. Accordingly, what is your k3 is hf x0 plus h by 2 your y0 plus k2 by 2. k2 already we got it here. So this is equal to hf 0.05 1.0455. If you simplify it, it will be 0.0909. Okay. Now coming to your k4 is hf x0 plus h y0 plus k3 is equal to your hf 0.1 1.0909. So this will be your 0.0832. So now by the formula, what is your y1 is y of x1 is y of 0.1, it is equal to y0 plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. So you substitute the value of this is k1, this is k2, this is k3 and this is k4. This is k4. If you substitute it, and this is final answer will be okay. If you substitute all these values, it will be 1.091167. If you round it up to 4 decimal places, it is 1.0912. Okay. Now coming to step 2 step 2 for n is equal to 1. Okay. What is your k1 hf x1 y1? So this is equal to h is 0.1 into y1 minus x1 by y1 plus x1. If you substitute it, it is 0.1. Your y1 is 1.0912 minus x1 is 0.1 divided 1.0912 plus 0.1. If you substitute it, the value of k1 will be 0.0832, and likewise here k2 will be hf x1 plus h by 2 y1 plus k1 by 2. So this is equal to hf 0.15 1.1328. So if I simplify, it is 0.0766, and here k3 will be hf x1 plus h by 2 y1 plus k2 by 2. Substituting the values, it will be h into f of 0.15 1.1295. So this is equal to 0.07655. And what is my k4 is hf x1 plus h yn plus k3. So this will be HF 0.2 1.16775. So this is equal to H is 0.1 into 1.16775 minus 0.2 divided by 1.16775 plus 0.2. If I simplify it, it will be at 0.07075. Okay. So now applying the formula. Now my y of 2 is y of x2 is y of 0.2 is equal to y1 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. If I substitute all these values, okay, now substituting all these values, we are getting this is here y1 from step 1, and after simplification it will give us y of 0.2 is equal to 1.167908. If we round up to 4 decimal places, it is 1.1679. So this is my final answer. Okay, final answer 1.1679. In step 1 it is 1 point this. Okay, similarly if it is asked find y of 0.345, then also we can continue more steps. You see, now coming to the summary. If it is asked solve this in the interval, suppose 0 1, then it is quite lengthy. It is quite lengthy. So this choice of h, we may choose choice of h as 0.2, or we may choose h is equal to 0.5. If I choose this, we need 2 steps to perform. If I choose this, we need 5 steps to perform. If I choose h is equal to 0.1, then we have to perform 10 steps, right? 10 steps we have to perform. So this is a lengthy approach, lengthy method. Okay, so better we should take it, right? That is up to your convenience if not given. So now, though you see this Runge-Kutta method is very lengthy, right? However, if we use computer programming, then this job is quite simple, right? Then it is quite simple. It is, since this formula is straightforward, it is quite easy to formulate the computer program. Okay, so but manually if it is asked, we should use the scientific calculators to solve it. Okay, so the video is getting lengthy, we should close it here. If you feel this lecture is interesting and helpful, please like and subscribe to this channel to boost my motivation. Thank you all. Have a nice day.